Okay, hi everyone, welcome back to this video series on Windows Server 2012. In this chapter, I will discuss the most important protocol used in Microsoft Windows Server 2012 R2 network, Transmission Control Protocol, Internet Protocol, TCP/IP. TCP/IP is actually two sets of protocols bundled together. The Transmission Control Protocol, TCP, and the Internet Protocol, IP. TCP/IP is a suite of protocols developed by the US Department of Defense's Advanced Research Projects Agency in 1969. This chapter is divided into two main topics. First, I'll talk about TCP/IP version 4, then I'll discuss TCP/IP version 6. TCP/IP version 4 is still used in Windows Server 2012 R2, and it was the primary version of TCP/IP in all previous versions of Windows. However, TCP/IP version 6 is the new release of TCP/IP, and it has been incorporated into Windows Server 2012 R2. Understanding TCP/IP, I mentioned that TCP is actually two sets of protocols bundled together, TCP and IP. These protocols sit on a four-layer TCP/IP model. Details of the TCP/IP model. The four layers of the TCP/IP model are as follows. The application layer is where the application that use the protocol stack reside. These applications include File Transfer Protocol, FTP, Trivial File Transfer Protocol, TFTP, Simple Mail Transfer Protocol, SMTP, and Hypertext Transfer Protocol, HTTP. The transport layer is where the two transport layer protocols reside. These are TCP and the User Datagram Protocol, UDP. TCP is a connection-oriented protocol and delivery is guaranteed. UDP is a connectionless protocol. This means that UDP does its best job to deliver the message, but there's no guarantee. The internet layer is where IP resides. IP is a connectionless protocol that relies on the upper layer The internet layer is where IP resides. IP is a connectionless protocol that relies on the upper layer, transport layer, for guaranteeing delivery. Address Resolution Protocol, ARP, also resides on this layer. ARP turns an IP address into a media access control MAC address. All upper and lower layers travel through the IP protocol. The data link protocols like Ethernet and Token Ring reside in the link layer. This layer is also referred to as the network access layer. How TCP/IP layers communicate. When an application like FTP is called upon, the application moves down the layers and TCP is retrieved. TCP then connects itself to the IP protocol and gets released onto the network through the link layer. This is a connection-oriented protocol because TCP is the protocol that guarantees delivery. When an application like TFTP gets called, the application moves down the layers and UDP is retrieved. UDP then connects itself to the IP protocol and gets released onto the network through the link layer. This is a connectionless protocol because UDP does not have guaranteed delivery. Understanding port numbers. TCP and UDP rely on port numbers assigned by the Internet Assigned Numbers Authority, IANA, to forward packets to the appropriate application process. Port numbers are 16-bit integers that are part of a message header. They identify the application software process with which the packet should be associated. For example, let's say that a client has a copy of Internet Explorer and a copy of Mail open at the same time. Both applications are sending TCP requests across the internet to retrieve web pages and mail respectively. How does the computer know which return packets to forward to Internet Explorer and which packets to forward mail? When making a connection, the client chooses a source port for the communication that is usually in the range 1024-65535, or sometimes the range 165535. This source port then communicates with a destination port of 80 or 110 on the server side. Every packet destined for Internet Explorer has a source port number of 80 in their header, and every packet destined for mail has a source port number of 110 in the header. Table 8.1 describes the most common port numbers. You might need to know these for the exam. You can visit www.ina.org to get the most current and complete list of port numbers. It's good to become familiar with specific port numbers because it's a benefit to be able to determine from memory the ports that, for example, allow or block specific protocols in a firewall. Allowing only port 80, for instance, does not ensure that all web traffic will be allowed. You must also allow port 443 for certain secure web traffic. Table 8.1, common port numbers. So I'll just have a quick look at these. Port number description: 20 FTP data, 21 FTP control, 23 Telnet, 25 simple mail transfer protocol SMTP, 53 domain name system DNS, 80 hypertext transfer protocol HTTP web, 88 Kerberos, 110 Post Office Protocol v3, POP3, 443 secure HTTP, HTTPS. Understanding IP addressing. Understanding IP addressing is critical to understanding how IP works. An IP address is a numerical identifier assigned to each device on an IP network. This type of address is a logical software address that designates the device's location on the network. It isn't the physical hardware address coded in the device's network interface card. In the following sections, you will see how IP addresses are used to identify uniquely every machine on the network MAC address. The hierarchical IP addressing scheme. An IP address consists of 32 bits of information. These bits are divided into 4 sections, sometimes called octets or quads, containing 1 byte, 8 bits each. There are 3 common methods for specifying an IP address: dotted decimal, as in 130.57.30.56, binary, as in 1000 0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.Line 1E. 38. All of these examples represent the same IP address. The 32-bit IP address is structured or hierarchical address as opposed to a flat or non-hierarchical address. Although IP could have used either flat addressing or hierarchical addressing, its designers elected to use the latter for a very good reason. IP address structure. IP addressing works the same way. Instead of the 32 bits being treated as a unique identifier, one part of the IP address is designated as the network address or network ID, and the other part as a node address or host address, giving it a layered hierarchical structure. Together, the IP address, the network address, and the node address uniquely identify a device within an IP network. The network address, the first two sets of the first two sets of numbers in an IP address uniquely identifies each network. Every machine on the same network shares that network part of its IP address, just as the address of every house on a street shares the same street name. In the IP address 130.57.30.56, for example, 130.57 is the network address. The node address, the second two sets of numbers, is assigned to and uniquely identifies each machine in a network, just as each house on the same street has a different house number. This part of the address must be unique because it identifies a particular machine, an individual, as opposed to a network. This number can also be referred to as a host address. In the same IP address 130.57.30.56, and the node address is .30.56. Understanding network classes. The designers of the internet decided to create classes of networks based on network size. For a small number of networks possessing a very large number of nodes, they created the Class A network. At the other extreme is the Class C network, reserved for the numerous networks with small number of nodes. The class of networks in between the very large and very small ones is predictably called the Class B network. The default subdivision of an IP address into a network and node address is determined by the class designation of your network. Table 8.2 summarizes the three classes of networks, which will be described in more detail in the following sections. So we'll just take a quick look here. Table 8.2 network address classes. So class, mask of bits, leading bit patterns, decimal range of the first octet of IP address, assignable networks, and maximum nodes per network. So class A, 8, 0, 1, 126, 126, 16, 7, 7, 7, 214, B, 16, 10, 128, 191, 16384, 65, 534, C, 24, 110, 192, 223, 2097, 152, 254. To ensure efficient routing, internet designers defined a mandate for the leading bits section of the address for each different network class. For example, because a router knows that a Class A network address always starts with a 0, it can quickly apply the default mask. If necessary, after reading only the first bit of the address, Table 8.2 illustrates how the leading bits of a network address are defined. When considering the subnet mask between network and host address, the number of bits to mask is important. For example, in a Class A network, 8 bits are masked, making the default subnet mask 255.0.0.0. In a Class C, 24 bits are masked, making the default subnet mask 255.255.255.0. Some IP addresses are reserved for special purposes and shouldn't be assigned to nodes. Table 8.3 describes some of the reserved IP addresses. See RFC 3330 for others. Okay, so Table 8.3, special network addresses, address and function. Entire IP address set to all zeros, depending on the mask. This network, that is the network or subnet of which you are currently a part, or this host on this network. A routable table entry for all zeros with a mask of all zeros used as the default gateway entry. Any destination address masked by all zeros produces a match for the all zeros reference address. Because the mask has no ones, this is the least desirable entry, but it will be used when no other match exists. Network address 127 reserved for loopback tests designates the local node, and it allows the node to send and test packets to itself without generating network traffic. Node addresses set to all zero, used when referencing a network without referring to any specific nodes on the network, usually used in routing tables. Node address of all ones, a broadcast address for all nodes on a specific network, also known as a bidirectional broadcast. For example, 128.2.255.255 means all nodes on a Class B network. 128.2 routing this broadcast is configurable on certain routers. 169.254.0.0 with a mask of 255.255.0.0. The link local block used for auto configuration and communication between devices on a single link. Communication cannot occur across routers. Microsoft uses this block for automatic private IP addressing, APIPA. Entire IP address set to all ones, same as 255.255.255.255, 10.0.0.0/8, 172.16.0.0 to 172.31.255.255. Broadcast to all nodes on the current network, sometimes called a limited broadcast on all ones broadcast. This broadcast is not routable. 192.168.0.0/16. The private use for classes A, B, and C, as noted in RFC 1918, the addresses in these blocks must never be allowed into the internet, making them acceptable for simultaneous use behind NAT servers and non-internet connected IP networks. Class A networks. In a Class A network, the first byte in the network address and the 3 remaining bytes are used for the node address. The Class A format is network.node.node.node. For example, in the IP address 49.22.102.70, 49 is the network address and 22.102.70 is the node address. Every machine on this particular network would have a distinctive network address of 49. Within that network, however, you could have a large number of machines. There are 126 possible Class A network addresses. Why? The length of a Class A network address is 1 byte, and the first bit of that byte is reserved. So 7 bits in the first byte remain available for manipulation. This means that the maximum number of Class A networks is 1 to 8. Each of the 7-bit positions that can be manipulated can be either a 0 or a 1, and this gives you a total of 27 positions, or 1 to 8. But to complicate things further, it was also decided that the network address of all zeros, 0, 0, 0, 0, 0, 0, 0, 0 would be reserved. This means that the actual number of usable Class A network addresses is 128 minus 1, or 127. Also, 127 is a reserved number, a network address of 0 followed by all ones. 0, 1, 1, 1. 1111. So you actually start with 128 addresses minus the two reserved, and you're left with 126 possible Class A network addresses. Each Class A network has 3 bytes, 24-bit positions for the node address of a machine, which means that there are two 24 or 16 777-216 unique combinations, because addresses with the two patterns of all zeros and all ones in the node bits are reserved. The actual maximum usable numbers of nodes for a Class A network is 24 minus 2, which equals 16, 7, 7, 7, 2, 1, 4. Class B networks. In a Class B network, the first 2 bytes are assigned to the network address, and the remaining 2 bytes are used for the node address. The format is network.network.node.node. For example, in the IP address 130.57.30.56, the network address is 130.57 and the node address is 30.56. The network address is 2 bytes, so there will be 216 unique combinations. But the internet designers decided that all Class B networks should start with the binary digits 10. This leaves 16-bit positions to manipulate. Therefore, there are 16 384 or 214 unique Class B networks. This gives you an easy way to recognize Class B addresses. If the first 2 bits of the first byte can be only 10, this gives you a decimal range from 128 up to 191 in the first octet of the IP address. Remember that you can always easily recognize a Class B network by looking at its first byte, even though there are 16 384 different Class B networks. In the first octet in the IP address falls between 128 191. It is a Class B network regardless of the value of the second octet. A Class B network has 2 bytes to use for node addresses. This is 216 minus the 2 patterns in the reserved executive exclusive club, all zeros and all ones in the node bits, for a total of 65.534 all possible node addresses for each Class B network. Class C networks. The first 3 bytes of a Class C network are dedicated to the network portion of the address, with only 1 byte remaining of the node address. The format is network.network.network.node. In the example IP address 198.21.74.102, the network address is 198.21.74 and the node address is 102. In a Class C network, the first 3-bit positions are always binary 110. 3 bytes or 24 bits minus 3 reserved positions leaves 21 positions. There are therefore 221 or 2097152 possible Class C networks. The lead bit pattern of 110 equates to decimal 192 and runs through 223. Remembering our handy, easy recognition method, this means you can always spot a Class C address if the first byte is in the range 192.223, regardless of the values of the second and third bytes of the IP address. Each unique Class C network has 1 byte to use for the node address. This leads to 28 or 256 minus the two special patterns of all zeros and all ones for a total of 254 node addresses for each Class C network. So I'm going to leave it here today for this video. If you like listening, please consider sharing and subscribing. Thank you very much, everyone.